First, a couple of confessions. The first time I heard about minimality was yesterday. I have never worked on the swampland program. And the last time I wrote a paper with Calabi-Yas in it was about 15 years ago. So I think I'm sort of the ugly duckling in this company of swans. And I was given the job, probably impossible, of explaining a different kind of attitude and approach towards notions of complexity.
Actually, ugly duckling fits with swampland.
What's that? Duckling. Yeah, you use the phrase. Yes, exactly. Well, okay. From then, I'm part of the swampland program. Right. So, yes, I was given the task of trying to explain some of these ideas that have become prevalent in the field, in other branches of string theory, about the complexity of quantum dynamics. Part of the reason that's an impossible job is there's a substantial number of papers from just my group alone. To the best of my knowledge, nobody in this room has worked on this. So the approach I'm going to take is to sort of introduce the ideas, start with basics, and if I don't get to the end of my talk, it's totally fine. Let's just go through whatever seems interesting to people, and I don't have to get to the end of my talk. That's the approach I'm going to take. Feel free to ask me questions, and if I feel I should defer them, I will. So the topic I want to talk about is complex dynamics in quantum systems, the word complex being important here. And in the rest of physics, so to say, this topic has become interesting or important the last 5-10 years for several reasons. So one reason is because people are working on problems in quantum computation where it's a matter of great importance of whether in some intrinsic sense, some computation is complex in some appropriate way or simple, because that makes a difference to whether you can build a thing to compute it. It's also become important in the study of dynamical phases in systems out of equilibrium. So very often in physics, we study things that are equilibrium and are not really changing in time, and you characterize them. But when things are changing in time, it could be that some kinds of things are more complicated than others. So what does that mean? What effects does that produce? Well, that is related to the general problem of characterizing chaos and its supposed contrasting case, integrability in the dynamics of quantum systems. We'll discuss later why that's actually difficult to do, unlike much more so than in classical systems. And it's also become a very important question in problems in quantum gravity and various puzzles about black holes, which were alluded to by various people. Now, I think the reason why I was asked to speak here is that in many of these situations, there is some essential tension between some kind of singular continuum description and a true underlying finiteness in the system, which you have to somehow resolve to get to the proper physics of the thing. So I think that is the source of thing. But we won't talk very much in that language, because that's not the way into the subject for most people. Yes, please.
A bit more about what you mean with integrability?
That is a difficult question to answer, as we will discuss later. So integrability, classically, even quantum mechanically, integrability classically supposed to mean that you can solve completely the equations of motion in terms of some integral. So you have to say x is equal to some integral of something, and you're done. That's what would be regarded as the solution, right? And if you have enough integrals of motion, then in principle, up to doing the integral or putting it in the computer, problem is solved. It's actually more subtle than that in quantum mechanics, because there are many, and also classically, because there are systems that are intermediate between being maximally chaotic and integrable. So this is a subtle subject. So I'm placing a dichotomy which is not quite so clear in real systems. Yeah. Yeah? Okay, so let me give an example. You should see an example of why we care about this kind of thing. And clearly the most exotic thing we could talk about here is the quantum gravity and black holes. So I'm going to talk about a couple of puzzles regarding black holes, right? So here we go, some examples of black hole puzzles. So the first question is, what is a black hole? Ta-da! So this is for the benefit of the mathematicians, because I think the physicists all know. So a black hole, for our purposes, is just a particular solution to the equations of general relativity. This is written in the language of a line element, which I think mathematicians hate. But anyway, it's very useful to us because it's the analog of the Pythagorean theorem. So in this formulation of the line element of a space, you can see that when r equals g times m, if you like, everything looks a bit singular. And that looks singular. This should have been r equals g times m. That looks a bit singular, but that's really, but it isn't. That is a coordinate singularity that was understood years ago by Kruskal, I think, an applied mathematician. And then what you can do is you can maximally extend this classical solution. it's a bit difficult to draw the whole thing. So what you do is you draw a conformal diagram. And a conformal diagram is you draw a picture of the whole solution with some conformal factor removed, right? Some overall scaling factor. And this can be infinite in some places. And you get this as the conformal diagram. In this conformal diagram, this is the future, this is the past. In the far future, there's a singularity. That's one place where issues of finiteness, lack of finiteness, and that stuff comes in, because what the hell is a singularity? Then there's a horizon. The horizon is a region, bounds some region of the space and time behind which you can't resolve, well, an external observer can't see what's going on. That's another very weird thing. Whoever heard of that you hide information in it, and that's implicated in some of these cobordism conjectures and things of this kind. What is this space-time? Well, you can take a slice through it, and if you examine the slice through it and sort of draw it out into what the picture of the space looks like, I've removed the conformal factor or reinserted it, it looks like a wormhole. So here's asymptotic infinity. You come in towards the middle, and there's a kind of throat, a wormhole, if you will, an Einstein-Rosen bridge going between two asymptotic regions. And as time passes, this wormhole grows longer and longer. But that's the solution. This is an eternal black hole. It exists forever. It's actually a wormhole solution. It's a thing that was originally written down by Schwarzschild in 1916 or something. You can also make these things from the collapse of a star. That is a complete and total headache, and we won't do it because I don't like headaches, right? So famously, a point that's come up in the swampland kind of discussion is that a black hole is supposed to have an entropy, and the entropy goes like the area divided by 4g Newton h bar. Notice the h bar, which is the Planck's constant in the denominator, when h bar goes to 0. So you have a classical world. This thing is going to infinity. So the standard statistical mechanical interpretation of entropy then implies that you expect e to the s to be the dimension. Well, I wrote quantum gravity microstates, but really e to the s, this huge number, should be the dimension of the underlying Hilbert space of the theory. The Hilbert space of quantum states has this dimension, which is, completely invisible in this continuum classical limit. So you'd like to know where that came from. So I'm going to enumerate several puzzles that are related with finiteness, discreteness versus this continuum description, and then we're going to get into the game. Right, so here's one. Wait, this wasn't the puzzle. So I wrote this in this way so that I can just sort of expand these things and not expand them if I don't want them. So here's first puzzle. Why can't you see the microstates when you're far away? So if this is a good quantum theory like string theory or something that makes the system, then you have lots of microstates that explain the entropy. So why can't you see them? See, one class of answers to this is they're just too complex to be seen by standard simple probes for which you normally build physical theories. That physical theories are built to describe simple probes, but the state is too complex for that. Here's a way of thinking about that, right? So this is a model of the idea, if you like. So you say, here are the black microstates of some gigantic black hole, and I've put some technical conditions about which space it is in and stuff that the mathematicians don't need to care about. There is some known duality that tells you how to construct the relevant microstates. For our purposes, it suffices that all you do is that there is some vacuum state, some minimal state in the Hilbert space of states of this theory, and you apply an operator to that state to make this kind of microstate, right? That's what you're supposed to do. And there is some understanding of what these operators look like. So in this theory, there are some fundamental fields. There's some gauge field, there's some scalar fields, there's some fermions, and the way you make operators, like in any quantum field theory, so this is a quantum field theory description of the microstates of the system, right? So the way you're supposed to make a state or make an operator is you take the fundamental fields, which are like letters in an alphabet, you multiply them all out, and if you've got some gauge symmetries and everything, you may need to take some traces and what have you to make the thing gauge invariant. So this trace is standing in for whatever you do to make the thing gauge invariant. The point I want to make is, n, if the mass m is large, then you need, it turns out, this is an SUN gauge theory here with order n squared, and the dimension of this operator is order n squared. That basically means, for our purposes, that you need to use n squared letters in this very long word, and n is going to infinity. So the question is going to be, is n infinite or is n finite, right? So let's suppose n is very big. You know what's going to happen, right? Almost all long strings made from a finite alphabet look random. They're very complicated from the point of view of trying to piece apart where they are. They're very complicated from the point of view of Kolmogorov complexity. If I told a Turing machine to compress this string that makes this long operator to be small, you wouldn't be able to do it very well because there's no structure in it. So at some point, in some way, this is the heart of why you can't resolve these microstates. In fact, you can go further. There are theorems, right? So if I tell you I have a finite alphabet, and I tell you, you make a very long string out of it, and then I tell you, please tell me the probability, if I pick a random long string, if I just pick a string from a bag, what is the probability that it deviates from the uniform distribution of letters? There's a theorem, Sano's theorem, that tells you exactly what the deviation, this large deviation theory, it'll tell you what the probability is. It's tiny, and as the strings get larger and larger, it goes exponentially to 0, right? So the lesson there is you would be forgiven if you have small probes and to say, well, I don't care, let n be infinity. This is a gigantic state. And there's no way you'd be able to resolve the details. So you'd have to do very complex operations to resolve the state. So in this way, the word complexity, in some meaning of that word, appears in this kind of problem. Okay, so that's one thing I want to mention. And we'll see how it relates later to some of the things I have to say. Yeah, Matilda. Oops.
To think of these very complex operations.
What's that?
How am I supposed to think of these very complex operations? I mean, I understand the CFTs on the boundary.
Right. So we'll discuss this later. So actually, in the boundary CFT, you have some very complicated probe for which some other very long operator for which you're producing some two-point function. I have actually 2 papers recently with 2 graduate students. One is Tom Yildirim, who's at Oxford, and Will Chan, who's at Penn. Basically trying to redo those calculations from the bulk point of view, where you introduce some kind of shell of matter and you do this, that, and the other, and you compute wormholes and quantum gravity. And many of the qualitative words that I'm saying here work out rather nicely. So it's the kind of problem which is like an NP problem. The quantum analog of an NP problem is QMA. So quantum Merlin-Arthur. It's the kind of problem where if I tell you what the state is, you can check it easily. But if I don't tell you, it's hard to find the state, right? It's that kind of problem. Yeah. Okay, so let me give you another one. This one, instead of the many puzzles, I think I'll only do 2 puzzles, and then I want to stop and move on to the actual content. Here's another puzzle. There is this annoying singularity. What is a singularity? Well, in this kind of geometric description of things, a singularity is a place where, let's say, the curvatures blow up. That's, you have some figure of merit for what makes it singular. That is completely annoying to physicists because it implies a breakdown of the equations describing the world, lack of predictability and everything, so it breaks the basic promise of what physics should be like. There's a singularity also in the past and the future. The past is even worse in some ways because it means you can't really specify initial conditions, really, at the beginning of time. That sucks. Okay, so what does this mean? So a possible answer that you will see, we will allude to towards later, there's some hint of now, at least in lower dimensional theories of gravity, is that quantum gravity dynamics is chaotic, and that kind of chaotic dynamics makes wave functions, quantum wave functions, in a certain sense, exponentially complex, okay? And then simple continuum classical descriptions simply do not see the details to resolve the state, and so the effective description in this situation where there was an underlying discrete thing somehow with a wave function on this Hilbert space, and you forgot about it, it just looks singular because you're extrapolating the wrong thing. It's like taking an analytic function and there's some expansion of the real line, you drop some higher order terms, and then you extrapolate, it could look totally bad on the, on the imaginary line because you forgot some terms that were important for the extrapolation. It's that class of explanations, okay? And which involves the chaoticity and the complexity, in a sense that we will define, of the wave function. Okay, so those are 2 examples. There's another one involving the growing volume of the interior, which I think I'm going to skip these 2 in view of the time. Anyway, I'll come to you in a second. So to discuss these things more precisely, as well as these things, which I didn't talk to you about, right? And I won't unless you ask me. Really, one of the things we've got to do is I keep throwing this word complexity around as though it's a thing. Well, I need to make it a thing by giving it a definition. So what we're going to do, and so that has been an effort of many years now, several 5 years, let's say, by various people. And so I'll tell you a little bit about the kinds of efforts, kinds of definitions that people have tried and what's come out of it. That's going to be the goal for the remainder of the talk, yes? And then at the very end, I will describe very quickly and rather schematically applications to these puzzles. Question?
Yeah, so about the thing about the singularity, is
Yeah.
that related to this recent work about like mini superspace quantization of the BKL model? I
Yeah.
think it was like people like Sean Hartnell maybe.
Yeah, so can we come back to the BKL model at the end?
Sure.
So it's you can definitely mini superspace do things. And indeed, the BKL thing involves these kind of rapid oscillations in time as you come closer. I will not actually talk about that. I'll talk about something different that well before you get to the range where the thing starts to spin around really, really quickly, there's a breakdown, I will try to claim, in the classical description because the wave function has become very complex. The classical geometry hasn't. It's all smooth and nice and very far from the singularity. But in the special cases of low-dimensional gravity where you can solve these things, you'll see that if you follow your nose, it's become very complex. And then you should ask the question whether you should have believed the classical extrapolation past then and the BKL things. That's a question that I'm still thinking about, and that's not a definitive statement, therefore. Yeah.
Maybe say 2 words on the volume growth.
Yeah. Oh, can I say 2 words on the volume growth? Okay, because it motivated quite a lot of work. Let me say, so it's more than 2 words. So the reason why I was just asked to talk about this is actually this was a heavily motivating factor for much of the field. So that's why you want me to talk about it. Here's the thing, right? So this is the black hole. This is, again, this conformal diagram. I'm going to ask you to accept that you understand what it is. So you take a slice through it, and that is one of these sort of wormhole kind of pictures I drew. Here's another one. And let me say I examine the length of the thing passing through here. And here's another one, and the length keeps getting bigger and bigger. So the volume of the Einstein-Rosen bridge on a maximal spatial slice, well, okay, so this keeps growing, okay? So this thing is a diffeomorphism invariant quantity. I tell you these 2 points, I ask you for the maximal spatial slice connecting them, and then I can find out this bit of it. So the setting of drawn is one where there's a description of the space-time in a dual quantum field theory. That is this ADS-CFT correspondence that I think various people have alluded to. So it turns out that in such a duality between 2 theories, any quantity that's gauge invariant on one side, that is to say, is a well-defined measurable quantity, should have a description on the other side. So the question is, in this dual description, what is the quantity that equals the volume of the wormhole? Because that volume is a diffeomorphism invariant quantity, therefore should have a good description, right? So the puzzle is that if you take for granted this classical description, it keeps growing forever, and it's extremely difficult to imagine a quantity that grows forever. Actually, it's very difficult to imagine a quantity that grows past what's called the thermalization timescale of a theory, because everything's come to equilibrium. And what are you going to measure that's going to keep changing further in time? So there was a proposal really due to Susskind that there is a thing in the quantum field theory that ought to be able to grow past the thermalization timescale, and that is the complexity of the state. And so maybe somehow this volume is equal to that complexity, right? That was the conjecture due to Susskind. The problem, of course, is, well, that's very nice, but please tell me what complexity is, would be the issue, right? And so that wasn't defined in that conjecture. So that's another motivation for why we should go after that and try to see if you can give a meaning to the term. Let me just say that if you accept that conjecture, where is it? Did I put the same slide on again? I put the same slide on again, so I'll just tell you what, there are 2 predictions, right? One prediction, if it's true that there's some relationship between complexity and this volume, then the key prediction that you should keep in mind is you know that the underlying theory is some quantum mechanical, quantum field theoretic system with a finite entropy, because we already know the black hole has some finite entropy. So in any system that has a finite entropy, there's a finite dimensional Hilbert space. And there are any formulation of complexity anybody ever came up with says that that measure of complexity will saturate because, after you've made the thing as random as possible on the Hilbert space, there's nothing more you can do to make it more complicated. So this is a prediction that if you have the correct quantum analog of volume on the gravity side, that object will saturate at late times, that the volume will not grow forever. But there's a prediction there. I'll tell you something about that at the end. But was that sufficient? Okay, so these are all the motivations for why, another section of the field of string theory that doesn't work on the swampland has been interested in questions of complexity. I mean, the swampland people are interested for other reasons, right? Good. So let's start. So there are some intuitions that you can have. And because I took a lot of time with this motivation, I'm going to be quick with intuitions because I want to get to the actual formalism. So one intuition from computer science is basically that the complexity of anything essentially should be some measure that counts how many basic building blocks you need to make the big thing. How many small things do you need to make the big thing? How many Lego blocks do you use? So this goes back all the way to Kolmogorov, who said, you give me a number, its complexity is the size of the smallest Turing machine. You need to write it down. So for example, the number 3.565 is small because this doesn't take much space. Pi looks very complicated, but it's easy because there's a short program that'll produce it. But square root of 7, square root of 7 is simple, but a true transcendental number may not be so simple unless there's an algorithm to produce it. So that was the kind of idea there, right? It's the shortest description, right, in terms of a Turing machine. There's a variant of this in information theory called stochastic complexity, where you give me, let's say, an image and I compress it and I find the shortest compression. So it's, again, the shortest description. So in computational complexity theory, the way this developed is, suppose I'm thinking of doing my computation using gates. So a gate is a function, an elementary function that you're going to use to take some set of inputs and produce an output. Then in computer science, you think about computing functions not additively, like in a Fourier series or a Taylor expansion, but compositionally. It's f of f of f of f of f, right? That's what they like to do. So this is, you compute some f's, then you stick them in as inputs into something else, some more f's. So it's compositions, and you draw them as a figure like this, and you draw a circuit. So in circuit complexity, you would say the complexity of a problem class is the size of the smallest circuits you need to solve it, right? Again, it's the minimal size of something. And I keep emphasizing this because there'll be various minimality things that will come in when I try to define in concrete terms what I want to mean by the complexity of a quantum dynamics. So I'm trying to justify that it's the minimality of the description that somehow is important. So there are ambiguities in any such thing. Well, what do you pick as your basic building blocks? You could pick a different Turing machine, you could pick different gates. And the way mostly computer scientists have dealt with this is by saying, well, I can't tell you a number, I can't put a number to the complexity. Rather, I will tell you classes. I will tell you scaling rule laws. In this class, no matter which set of gates or primitive operations you pick, well, I'll tell you that the complexity scales in the following way with the size of the problem. So that's their way of getting around it. In physics, we want something a bit more because if you're telling me the volume equals the complexity, then you've sort of committed in this language to a particular definition of the thing. So you'd like to work out what that definition may be. And maybe in physics, maybe there's some help with these ambiguities because, locality is a thing. It's easier to do things locally than far away. So you could introduce sort of aspects like that into your notion of complexity. Okay, so we're going to pursue, wait. Am I looking at the correct form of this? Okay, so I think I erased some slide, which is annoying. Okay, whatever. Now that it's erased, I'm just going to keep going. Okay, right. So the idea in computer science. So this I'm going to talk about method 1 for trying to talk about complexity. That was the slide that said this is method 1. Yes, I know what slide I'm missing. Okay, I'll draw it. So what do you want to capture? So what you want to capture is something like this. Suppose I have an initial quantum state that looks like that. And it evolves with time and it gets a little bit bigger or whatever. I would say that looks pretty simple, right? On the other hand, suppose I have this initial state, and then it becomes very bumpy, and it's entangled between here and here, and entangled between here and here. It's got multi-party entanglement, blah, blah, blah. I would say that's complicated. So you want some way of characterizing the difference between an evolution that does this and an evolution that does this, and hopefully put a number to it, right? That's the definition you're trying to come up with. So let's have a try. So one try in the physics context can be derived from an inspiration directly from computer science, okay? So in computer science, you might say, suppose I think about that as a quantum computation. That's the slide that's missing here. Suppose I think about this as a quantum computation, right? So what do? I say I start with initial state, and then I apply the time evolution operator, and then I do it again and again and again, and it evolves over time. Well, I might say that the complexity of the transformation is the minimum number of simple pieces needed to build it. Here's a picture of it, okay? So you have to remember, again, this is for the mathematicians, that in quantum physics, you describe a state as a vector Rayleigh array in a Hilbert space. The time evolution rule is you apply some operator to the initial state. That operator looks like the exponential of something Hermitian, and therefore it's a unitary operator. And so basically, time evolution is motion on the unitary group. Here I'm thinking about the operators that I'm applying. And the operators follow some trajectory on the unitary group. Let's say SUN, right? I've removed the overall phase, so that's why there's a U1 that's missing there. So it's a motion on SUN. Now, there was a very beautiful paper by this gentleman, Nielsen, who showed that if you think about this motion, see, in computer science, they do discrete steps. Apply, apply, apply. And here I'm talking about it continuously, just like we would in physics, right? There's a continuous motion. It so happens that Nielsen showed that there's a polynomial relationship between this geodesic length, the shortest length you take on the SUN manifold, between the initial point and the place where e to the minus IHT, the time evolution operator, gets you. There's a polynomial relationship between that and the circuit complexity, if you wanted to actually build a circuit. And for us in physics, the continuous notion seems a lot nicer, right? You just should see what is the shortest path, okay? So we're going to build this object. Hold on one second. Let me finish the narrative about this. So we're going to declare complexity to be the length of the geodesic between the identity, where you start, and this operator e to the minus IHT in a particular metric, right? The metric has to somehow separate things that are simple, the simple building blocks, and complicated. So for example, you could take the Cartan killing form of the group. That's supposed to be this thing. This is the simple piece, those directions are weighted by 1, and you take the complicated piece and you put a big weight on it to say how complicated it is. And you could modify this in various ways, yeah? You could modify this to say, well, you just separate into 2 classes, simple and complex. Well, maybe a function that acts in 3 qubits is only a little bit more complex than 2 qubits. Maybe 4 qubits is even more. You could grade this in some way, and people have studied many different options for that kind of thing. Yeah.
So does this notion of complexity depend on some kind of choice of basis? Like, is there, like, somehow I could imagine that you have some vector in some Hilbert space, and then in one basis, you can describe it using these simple quantum gates, and then you change to a different basis, and it becomes very complicated.
So it's basis independent on the state space, but it certainly depends upon what you think simple gates are. Right, so for example, a standard choice in physics would be something that acts on less than k qubits is simple, more than k qubits is hard, because if you ask Quantinuum to build a thing that has to simultaneously act on 8 qubits is much harder than doing 2 qubits. So you just use it to model that, right? But you can pick whichever, pick your poison. Make your decision as to what's simple and complex, and then you can feed it into this. And it'll absolutely matter.
So you have some natural choice from physics that you're saying that these are.
So in physics, I would say natural choices are that acting on fewer qubits at the same time and acting more locally is generally speaking going to be easier for you. That seems natural.
Like a qubit for you is like a spin or something?
Yeah, like the quantum spin. I'm trying to keep that abstract, but it's a quantum spin. The precise connection to the gravity problems is not clear here. So we'll talk about that separately, right? Okay, and so we're going to take also everywhere, we're going to assume that the Hamiltonian, the thing that generates the time translations, is one of the simple operators. Yeah.
So is this complexity invariant under S duality?
S duality, for God's sake. Where did I talk about string theory here?
Talking about n equals 4 superior mills, right?
No, that was a long time ago. This is an abstract statement. There's an abstract statement about unitary evolution on some Hilbert space. Please don't ask me about S duality. I have no idea. Okay. That is actually, but having said that, having dismissed the question like that, it's an extremely interesting question. It's an extremely interesting question to ask whether, for example, duality transformations, which are typically highly non-local, right, and mix up all the fields in crazy ways, whether these kinds of notions of complexity are invariant under them. I would almost bet the answer is no, because if I think about classic duality between electric-magnetic duality, which changes magnetic monopoles into point particles, right? It's something like that. Well, the magnetic monopole is a hell of a complicated thing compared to a point particle. So what's up with that? So no one, to my knowledge, has studied that. An opportunity for you. Yeah.
So if you define complexity as the minimal effort in calculating or doing something, that's by definition duality. So in other words, in the physics jargon, if you're in some frame and asking a question, which is much harder than in the framework you're doing it, the dual description is the simplest one. So that's
Yeah. So if you include duality as one of the operations you can do, then you should go to the simplest dual frame. But I think the question was posed in the language of, I've told you here are my elementary fields, do my calculation for me.
No,
now
that means you shouldn't do that. Otherwise, it's not an invariant concept.
That's the question, right? If I tell you,
It's a bad notion. It's just like.
if you say so, right?
No, sorry.
And if I personally think I'm living in a world where there are electrons.
But then I wouldn't trust your notion of complexity.
Feel free.
It just depends on frame of reference.
Totally, right? I'll do stuff that's basis dependent, frame dependent, everything. Because you know why?
Why?
I work in the trenches. So I use bases all the time. I have no problem asking how complicated it is to calculate the basis.
But invariant. It's like
Well, I didn't say it was invariant. I didn't say it was invariant.
Why should I take?
I'm asking, don't, feel free. I'm just telling you, feel completely free, right? I'm just telling you the notion that's being articulated, right? And at the moment, there's no notion of duality because this is being done on an abstract Hilbert space in this way with a particular Hamiltonian. You're asking me if the answer is duality invariant, and I don't know, right? And it may not be. Later on, we will talk about sort of minimal choices of bases and stuff like that. But the set of operations you allow in the construction of that minimal thing is really the question you're asking. Are duality transformations to find the correct dual frame allowed too? I would say the answer is yes, but I will also tell you that there's no literature on that, right? And so if you think that that means without that literature, this is not interesting, totally fine. Yeah.
So there's a claim here that there's a polynomial relation between the circuit complexity
Yeah.
and the level of Juliet, but you're saying, okay, for the circuit complexity, I should choose some
gate
gate,
that.
so you have to also, is the claim that
So-
for every choice of circuit, you can choose a metric?
So I don't know that literature in great detail, but I think really the answer there is it's all polynomially related. So usually the circuit complexity people would say, you give me a different reasonable gate set, there'll be a polynomial relationship between them anyway. So polynomial, 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 so they're all polynomially related.
So you care about this thing even beyond this polynomials?
Well, I will. I would want to. But with this method, I'm trying to describe two methods, right? This method is the method that everyone tried first, including us, that's coming out of computer science. As you'll see, we'll be able to prove many interesting things about it, but I actually don't think, it's not the thing that winds up equating to volume. But nevertheless, there's lots of interesting information here. So I think it's important to put it out, including the ones that were just asked about duality, right? Yeah.
The volume is obviously invariant.
I have to keep going. I have to keep going. Right. So I didn't say that this was equal to volume. There'll be another notion later that we will discuss. Right. So again, the mission I was given is not to describe my most recent work. The mission I was given was to explain what's going on in the field. So that's what I'm going to do. Okay. So then what you do is you want to compute geodesics in a group manifold. You have to write down, the geodesic equation. This is the geodesic equation in Euler-Arnold form, where F are the structure constants of the group. Well, you've got to write down the path length is, you solve the geodesic equation, and then you compute the length. This is the formula for the length. And when you do that, this is the unitary transformation, and this is the formula for the length. I'm just doing geometry on a group manifold, and that's supposed to tell you what the complexity is, right? So you can show, it's very easy to show that if the Hamiltonian is one of the simple operators, then initially this entropy, this complexity will grow linearly. Going back to what you were talking about, the volume, indeed, the second prediction coming from the volume equals complexity thing is that complexity will grow linearly initially. You should not take that to be any kind of proof that this is the correct notion of complexity, because essentially any notion of complexity will give you initial linear growth. Okay, so what can stop the linear growth? Right, two things. One is geodesic loops. Namely, you're going this away with the Hamiltonian, but there's a shorter path this way. Those are very hard to do in SUN because that thing is some complicated fiber bundle if you're past SU2 to SUN for some large N. It's really not known how to work out all the global geodesics, globally, how to work out these geodesic loops. There's another kind of obstruction that can happen, which is a geodesic, a conjugate point. A conjugate point is the thing where, you had a geodesic, but if you poke it a little bit, it doesn't change the length. So you can keep poking and wind up at some shorter geodesic. And there's a method for calculating that. So we're going to study those because we can, right? Okay. So what happens is the following. So what you do is you start with some initial trajectory, you perturb it, you stick it in the Euler-Arnold equation, and you get something called in the Jacobi equation, right? We don't need to understand the details. I'm just trying to illustrate that there's a way of doing this. There's some equation that finds out that looks like this. And what you need to do is to ask if the Jacobi equation can be solved in such a way that you start with the same initial point and you wind up with the same final point. And that'll tell you if there's a perturbation that you can put in that gets you a shorter distance. So it turns out that using that equation, you can show many properties that a theory must satisfy in order to, wait, have I been talking 45 minutes? No way.
No, we started late. Yeah.
Okay, otherwise I'm toast. Right, so you can show that that there are many properties of the theory that control whether or not these conjugate points exist. So one is that if the Hamiltonian, the time evolution operator, has an adjoint eigenoperator with some eigenvalue, lambda, then you can show that a conjugate point appears at these times. And if this operator is non-local, by which I just mean it's complex, because here we took the definition of being complex to be not locally acting on the bits, then you find out that conjugate points occur at this time. So this gives you a practical way of trying to check whether these conjugate points will arrest the linear growth. So it's just a practical method of doing a calculation. There's another thing you can do like that, where if you write down this matrix and it has a zero mode, then you can use the zero mode to determine whether there's a conjugate point. There's very physical criteria. Some of you are physicists. So there's a criterion that says that suppose the following object, right? Consider the following object. This object is you take all the simple generators, you compute their matrix elements and square it, and then you sort of normalize in some way. So it turns out that if this thing is exponentially suppressed in the entropy, then you can guarantee that the complexity growth persists for exponential time. So that you can write down results like this. This is hard work to find, but you can find them, which is the nice thing about it. Now, for those of you who are physicists, this will look very similar to the eigenstate thermalization hypothesis. There's a very similar kind of thing that goes on there. Basically, what this is saying is that you can't take an energy eigenstate of the system, a state with definite energy, and turn it into another state that has a definite energy by the action of simple things. That to turn one energy eigenstate into another energy eigenstate, you have to work hard. It'll be a complex operation to convert one to the other. That's what this condition says. And you can go on like this, and you can show that for integrable versus chaotic theories, this is a proof by example, by working out many examples, you can see that the integrable theories truncate their complexity growth in polynomial time, and the chaotic theories, by this definition of complexity, keep growing for a very long time. Right? That doesn't answer the question about duality. This is just sort of abstract results regarding motion in the Hilbert space. I cannot tell you about the invariances. Okay?
Just for understanding, are these computations done in infinite dimensional Hilbert spaces,
Yeah.
or are these finite dimensional?
all of these calculations are done in finite dimensional Hilbert spaces and then extrapolated to large n, right? So all of these things are being done. There are sums everywhere. So if this wasn't, and the sum has some very large n over there. So the intersection with some of the ideas that are going on here is when you work with quantum, maybe I have this, yeah. When you work with quantum field theories, there's infinite dimensional Hilbert spaces. And if you're working with infinite dimensional Hilbert spaces, there are many subtleties that can happen with this kind of analysis. And that is in fact the outstanding problem in this area, right? So these results that I just described are the state of the art, right, at the present time. The difficulty is to extend them to quantum field theories, especially because it's the quantum field theories that have some relationship to the theory of gravity. Okay, that's also one of the reasons why I can't really tell you about dualities, right? Because we're always talking about these sort of finite dimensional spaces. Okay? Okay, so given that, I'm going to talk about a second approach, right? So that's a roadblock. It's preventing progress in that direction. So the second way in which this has been approached is for people saying, well, what is the difference between a complicated and a simple dynamics? Well, a simple dynamics is one like this where, I take an initial state and I kick it and it kind of goes around little tori, it does some sort of simple motion. What's a complicated dynamic? Well, I know you kick it and it kind of goes everywhere. It kind of visits almost near everything. Maybe it's dense in the space of configurations, right? Ergodic in some way. So you might suppose that you could define the complexity of the dynamics in terms of, in some notion of ergodicity, right? Some notion of how the wave function spreads over time. And that is where the notion of a basis comes in, where, if I want to write down a calculation of how it spreads, I may need to do that in some basis. But actually, you can turn that into something a little bit more invariant in the following way, right? And this, I will answer this part of the question by saying, well, this will wind up being duality invariant in the right way, is what I will say, okay? So I'm going to say, which basis should you pick? Well, if I were Kolmogorov or Risson and somebody, I might say that for a given initial state, you should pick the basis that minimizes the spread over time. Let me explain what I mean. Obviously, if it's a pure state, at any time you can pick the basis to include that element. But that's not the game we're playing. You have to pre-commit to a basis. And so you start with some basis. And then over time, the wave function will have support in that basis. And I want at all times, up to some bound, presumably, that basis for all those times minimizes the support. So at time 0, and so that's going to be, and the spread complexity is going to be the measure of the spread. And the reason this is invariant is I've minimized, and then now, as you said, Kumran, right? So if the duality is one of the games I have to play here, well, if I apply a duality to some basis, well, I just get a different basis. So you should pick the basis that minimizes things. And indeed, this is duality invariant. Yeah, so I wanted to get to this as opposed to the computer science notion. Okay, yeah.
But if a theory is self-dual, we're defining duality as a redundancy.
Let's move the questions about duality to later, please.
Sure. Okay.
Because there is just so much left to say
Okay.
about this.
Just a comment.
Right. So in part because this is the approach that seems to be really widely used, and this approach with this measure of complexity, at least for two-dimensional gravity, there is a demonstration that it equals the length or volume of some wormholes in the appropriate theory of gravity. So this seems promising, so we should get a little bit further so you get a sense of what it is. And then we can come back. Is it okay? Okay. So I want to talk about what this thing is and how you compute it.
Again, the computation is finite dimensional. Again,
I'm again going to do finite dimensional computation, and that's going to be the same gripe I'm going to bring back at the end. And then I will briefly at the very end, because there won't be time, describe what happens when you take infinite n. And when you take the infinite, if you decide that the continuum theory is obtained by taking n to infinity in these things, what you will find is you will find a markedly different late time dynamics. For example, you may find that the complexity grows forever in this sense, rather than plateauing. And the differences between those two, I believe, are the secrets to many things, including why the description of the black hole past some time is just wrong, right? You should be thinking about it as a very quantum state that's very heavily spread out over some inherent finite dimensional, perhaps tame Hilbert space. I don't know, but those are the words I would be tending to use after having heard the things that I heard yesterday and this morning. Okay? So let me define the object. So let me remind you, quantum dynamics works like this. The time derivative of the wave function is the Hamiltonian acting on the state. Okay, so then I can expand it out in a Taylor series like this, where the psi n are nth powers of the Hamiltonian acting on the state, and let B be any basis for this Hilbert space. I'm going to quantify the spread of the wave function in this by finding the support of the wave function, this basis, square that to find the probability of being in any basis state. So that's some distribution. And then you tell me what measure you want. So the measure that everybody's been using for a while now is basically the mean of this distribution. But there are all the moments, there's the entropy, and they all have different interesting properties. We'll look at the mean as the first moment, and that'll have some interesting effects. Okay? Now, why is this the correct basis? If I work with discrete time evolution, it's trivial. Let me explain that. Real-time evolution is more complicated. We have to do some actual analysis to show that this is the answer. So in the discrete case, it's like this. So it turns out that the minimizing basis is the so-called Krylov basis, which is the Gram-Schmidt orthogonalization of the things. That's what you'd expect, right? How does this work? So, well, I'm going to pick the initial state to be my initial Krylov basis element. The state evolves. So I'll take the sort of orthogonal complement of the state, chuck it in, blah, 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 blah. Completely obvious, but this is the minimizing thing. Again, if you're doing continuous time evolution, the moment you have epsilon time, you have support and everything. So then there's a fuss and mess about showing why the actual support is minimized for some finite duration of time and so on and so forth. In our hands, we've only been able to show that up to some bound t, big T in the time. That's because we're doing Taylor expansions. And if we do Taylor expansions, well, the radius of convergence of the Taylor expansion matters, right? It's possible that this is correct throughout, but okay. So can you do this? So the next question is, can you calculate these things in a practical way? Because we need that if we're going to compute with volume. So I'm going to tell you several methods, right? I'll tell you about 3 methods and then move on to the applications. The first method is a so-called Langshos method or tridiagonalization method. There's a recursion formula developed by Professor Langshos already in the 1960s, and I'm so ashamed I didn't know this work. Right? There's this beautiful set of work by this guy Langshos. And when you're done applying this recursion formula, turns out the Hamiltonian acting on any one of these basis states, well, basically, let's skip this, takes this tridiagonal form. Basically reduces the dynamics to Markov on a chain. Right? So quantum dynamics in any dimension gets reduced to Markov dynamics on this particular chain with this tridiagonal Hamiltonian. And then you can compute whatever you want. So the recursion formula method is apply the recursion, put it on your computer, press go, or in special cases, like if you're doing motion on a group manifold, you can solve this analytically and write down what the answers are. Very beautiful formula you can get that involve various kinds of orthogonal polynomials built out of the Hamiltonian. You know, that's the kind of thing you'd expect. And that all happens in a very beautiful way, actually, here. Every classical orthogonal polynomial that you have ever known makes its appearance here in some extremely interesting way. Okay. Also, some orthogonal polynomials that aren't the usual ones. Then there's a second way of doing it. I'm just illustrating ways of doing this to show you that this is a completely practical technique. So what you do is you compute the survival amplitude. The survival amplitude is the probability for the state to stay itself. So here's this Markov chain. So, you know, what's the probability of staying here? Well, you know, if you do it once, well, that's the only way. If you do it twice, you can go around twice, or you can go around here and come back. Notice if I went around once, I only engage with this piece, with this amplitude, A0. If I go around twice, I engage with A0 and B1, right? So you can see what's going to happen is if you do this one by one, you're going to discover, one by one, you're going to discover a piece of information, the probability of staying in the same state, right? You're going to discover from it, as time passes, you're going to discover, well, the coefficient A0, then the coefficient B1, and then the coefficient B2, and so on. And all of these things are implicit, basically, in this quantity, which is equivalently the set of moments of the Hamiltonian in the initial state. So you give me the set of moments of the Hamiltonian in the initial state, and I will just work out through some dynamic programming algorithm, I'll just simply work out all the information about the tridiagonalized Hamiltonian, right? So it's a completely mechanical procedure that you can do in closed form for, you know, nice things with enough symmetry, and otherwise the numerics are easy, right? You can do it on your laptop. All right, that's method 2. Method 3 is rather beautiful, and it's connected intimately to random matrix theory. So method 3 says that I'm going to consider now the large N limit. That's where all of the subtleties about the large N limit versus finiteness come about. So in the large N limit, I can take the entries in this matrix, and the matrix index becomes a continuous variable. So it's two numbers, x and y. Okay? And in that limit, there's a formula relating the density of states of the theory, the density of energy eigenstates of the theory, to these various coefficients, these things called Langshaw's coefficients, which are the coefficients in this tridiagonalized Hamiltonian that then tell you everything you want to know about the spreading wave function. So there is a formula of this kind, and let me give you a schematic argument of how this comes about. And it involves an assumption of certain kinds of continuities and smoothness in the limit, right? So the way that works is, suppose H is the Hamiltonian, and you've tridiagonalized it. Now suppose that the tridiagonal coefficients have some continuous large N limit. Then you break up this whole Hamiltonian into little blocks, and because you've taken little blocks and the matrix is getting very big, and you've assumed that there's a smooth limit, right? You've assumed that there is a smooth limit. To assume that there's a smooth limit, in small blocks, the coefficients have to be constant. If they varied too quickly as you go down the thing, which can happen, by the way, you can absolutely write down systems in which these things have a much more jaggedy kind of feeling, where you can't do this. But if I've agreed that there is a smooth limit, then inside these small blocks, you will find the values are constant. But now I can immediately relate that, right? I mean, if I tell you I have a matrix which is tridiagonal, right, with constants along that, I can write down its eigenvalues in one line. And so that tells you the eigenvalues of this matrix, and the relationship of the eigenvalues here, 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 to these Langshaw's coefficients is the thing that leads to this formula. But that's the schematic version of the argument. The correct version of this argument requires a little bit more work. Take care of the limits carefully. Okay? And this formula can be inverted. How close am I to being out of time?
10 minutes.
10 minutes. Okay. So what I'm going to do, since I want to talk about applications, the last method here I'm going to talk about, I'm going to be schematic about it. So you can do one more thing. A classic example in physics of chaotic theories, theories with chaotic dynamics, are random matrix theories. So what you do is you draw your matrix from some matrix ensemble. That becomes the Hamiltonian that generates time evolution, right? So this is some large random matrix. Famously, as everybody in this room knows, if you take the large N limit of matrix models, many, many beautiful things happen, right? Eigenvalue spectra are known, lots of stuff. So our goal is I want to take a large N limit of a matrix model and then find out in that limit, can I write down a formula for this tridiagonalized Hamiltonian? Because the method that you have to do to compute the complexity here is not to diagonalize the Hamiltonian, but to tridiagonalize the Hamiltonian, a thing we're never taught to do in elementary quantum mechanics, but that is the form of the Hamiltonian relative to some initial state that allows you to compute the complexity, well, the spread of the wave function. So I'm going to skip the details, but basically generalizing some work of two mathematicians, Dumitriu and Edelman, you can sort of solve this problem completely. It's basically a saddle point kind of technique. You agree that these distributions become localized when the matrices become very large. You have to solve the saddle point equations, and you get some set of formulae. And at the end of the formula, you have some integral equations to compute. Okay? So we don't have to go through the details. I'm going to say one more method of quantifying complexity, and then I just want to describe applications which will hopefully be lighter than this barrage of formulae that's going past you. Okay? So another way of thinking about what is simple versus complex in a dynamics is that if I had simple dynamics and I take an initial state and I move it a little bit, it'll do a similar trajectory. Whereas a complicated, perhaps chaotic dynamics would be if I change the initial state a little bit and does some crazy thing, it's all sporadic, right? It's like kind of nuts. That should be complicated. Is there some way of characterizing that? So there's a nice way of doing that, which is that you take your initial state and you compute this Krylov basis that gives you its minimal description. Then you take your next state it's a perturbation of the initial state, and you compute the Krylov basis that describes its evolution. Then you take their overlaps. There's the matrix of overlaps between them. And from that, for every new state in your Krylov, in your special distinguished basis, you can compute the entropy of its support in the old basis. So I'm going to call that the coherence, and it is a measure of how, so suppose I kick a state a little bit, and I want to describe it. It says how delocalized that description will be in the old basis, right? You have the best possible basis, the most localized basis for describing the new state. You want to ask how delocalized this best possible basis is in the old state. So that's what this measure is supposed to be computing. Okay, so I've talked about three things, and I'm now mostly going to focus on the second and third one, right? Because they've turned out to be useful. The second one, characterize the complexity of a dynamics in terms of how much the state spreads across the Hilbert space. The second, this measure characterizes it in terms of, if I kick the state a little bit, how different the spread looks. So one is about the divergence of the description between two perturbed states, and the first one is about how ergodic or completely distributed the description is. All right, so let's just do a bunch of examples. So the first one is, well, okay, so you can consider chaotic theories, random matrix theories for the physicists, SYK models, etc. And if you compute these objects, you get a long linear ramp that's exponentially long, then it comes down and it flattens. And then there's some oscillations or not over here, and that depends upon the universality class, whether you're talking about unitary matrices, orthogonal or symplectic matrices in the Hamiltonian. So there's a very universal behavior of this kind for chaotic theories. That's the first statement. The second statement is, well, you can check this in more granular detail by looking at spin chains. So that's a series of, this is the Hamiltonian. You have a series of quantum spins that interact in some way. These two are known to be integrable in the senses that we discussed earlier. These two are known to be chaotic, okay? Or thought to be chaotic. Actually, the way in which people identify that is actually looking by the spectra of the theory. So in quantum mechanics, talking about stuff like, is there an integral of motion, doesn't make so much sense. So what you do instead, because that's not how you solve quantum theories. So instead, what you do is you work out the spectra, and chaotic theories tend to have a long tail distribution, and integrable theories tend to have a Poisson distribution of eigenvalues. But in truth, many systems are in between. Okay, so then what you can do is you can check the analytical formula that we gave. And it'll turn out that for the mean values of these Long-Shor's coefficients, the black lines, which are the analytical formulas, perfectly track the results. Both these theories, this is as you make the spin chain larger and larger. On the other hand, if you look at the variances in the around that mean, the analytical formulae that I described earlier perfectly track the development. But for the integrable theories have a much bigger variance thing. So that's where some of the differences between integrable and chaotic theories come about. Okay, so this is all to establish that we know what we're talking about with these systems. Okay, then you can go further. A classic kind of example of chaotic, non-chaotic theories that people talk about all over the place in the theory of dynamics is billiard systems. Billiard systems are like systems where there's some sort of wall, an impenetrable wall, and you sort of throw a ball in it, and the ball bounces around, and you look at the trajectory. Some things are integrable, some things are chaotic. There's quantum versions of this. So there's a class of billiards which are triangular, and the degree of chaos or integrability is controlled by the angles of the triangle, right? For some angles, it's integrable. Mostly, if it's irrational angles, for example, it will be chaotic. So this is supposed, you can study this, with dozens of examples and show a very beautiful correlation with the measures we're talking about and these things. This is all to establish this is a good measure. You can calculate it, and it correlates with what you want, okay? So the next thing is you can, this is a very nice thing, right? So this is using the last measure I talked about, this coherence, right? Namely, if you perturb a state, how coherent is the new basis and the old basis? How spread out is it, right? So here's what you find. So you can study motion on the group manifold SL2R. So you study a quantum particle that's moving around on the SL2R group. That's lots of symmetry, right? But that's a hyperbolic manifold. You can do it for SU2 or something called the Heisenberg-Weil group, which is in between. And if you measure this coherence, which is a measure of how spread out, the basis, the minimal description of the perturbed state is in the old description, here's what you find. For SL2R, which is paradigmatically chaotic, this, as you increase the Krylov index, the initial state is the same. This just goes mad, right? This is the exponential, actually, of the Krylov, of this thing that we were calling coherence. So there's an exponentially greater dispersion of the higher element. What's that?
It's the log or the exponential?
This is supposed to be the exponential.
Saying the growth is logarithmic? The exponential rate is.
This is the growth is exponential, so this is wrong. Okay. Yes. So we'll have to fix that in the paper, which we put last week. Thank you. Right. Whereas you see that for the integrable sort of examples, it's completely different. Right? So this is I would say that this is like one of the cleanest distinctions between chaotic and integrable theories that I have seen in quantum mechanics. Right? This is brand new off the I don't know. This is from a paper we wrote last week. So we'll be studying this further. Almost done. So now this is just going to be talk. So this is the discussion slide. Right? So I'm just going to talk about this, because it would require for the mathematicians, there's already been enormous amounts of technical things floating by, and this would require too much technical development. So I'm going to tell you just logically what happens. Remember I posed the problem of this wormhole volume, and does it grow linearly, does it saturate? So there is an example where you can check this completely. And that example is a certain kind of gravity in 2 dimensions called the Jakiv-Teitelbaum gravity. And it happens to have a relationship, known relationship with a particular large size limit, a continuum limit of something called the SYK model, right? So I'm not going to discuss any of the details. If you wanted to, we'd have to do all of this, so we're not. Okay? So in a certain limit in which the system gets large, it's known that these theories are related, right? So the classical gravity is related to the large system limit of this field theory, right? And that's a known thing. And in the early time situation, where the thing is all classical, there is a relationship that has been written down that equates, I mean equates, right? This isn't maybe is like, there's no similar sign, that equates the length or size of the wormhole geometries in these systems to the thing that I was calling the spread complexity. That's an equality. Okay? That is work due to Henry Lin, due to Scheer, Sonner, and Rabinovici, right? Beautiful. So in the early classical limit. So they worked in this limit because they couldn't solve the theory for finite n. The formulae that I gave you purported to give a method for solving the theory and measuring the spread complexity for finite n. So we do that. And then there are various random matrix theory classes that come in. There's some fuss and mess about which random matrix theory class you're in, and so on. And when you're done, what you find is precisely what you might have hoped or expected for, which is that the complexity measured in this way grows linearly at early times, exactly tracking the classical growth in the geometry. But at late times, it saturates, as it has to in the end, but you can calculate it. And what it tells you is that if you believe that the classical equality between the length in this space and the complexity extrapolates as is into the full quantum theory, you expect that at exponentially late times, the classical description is terrible. Right? The classical description is wrong because the wave function of the system has spread out over wormholes of many different lengths. It's not localized anymore. So you can't meaningfully talk about the length of the thing. And you shouldn't. There's something else that's much more, what you really should be talking about is the structure in the Hilbert space of the theory, not a particular geometry over there. That would be the lesson. So I'm going to end there. There's no real time to talk about this, but we could come up in discussion. So I was asked today to describe these 2 kinds of notions of complexity that have become prominent or much used over the last few years. So that's what I've done. So in the context of this workshop, and I'm sorry there was just so much material, but there has been a lot of work lately, so I didn't know what part which of you would be interested in. So I've tried to give you a complete overview. Now, there's a question of whether there's any connection between any of these things that have happened. And O minimality, tameness, and these notions of complexity that you were talking about. So during all of the talks, I kept feeling like there's a connection here, there's a connection here, there's a connection here, but couldn't put my finger on it. And the connection, I think, is basically coming about because all of these structures you guys are talking about have to do with identifying ways in which a system can have an inherent finiteness that may be invisible to you when you look at it in a different way. And that's exactly the kind of thing I was describing, right? So the classical gravity has an inherent finiteness underneath it because of the quantum Hilbert space, because that's the structure you should really be talking about. So if you don't talk about it that way, then you wind up getting all kinds of pathologies. So that I'll stop there.